the basic idea here that we're looking at is that moving charge causes magnetism. Moving charge causes magnetism. All right? If we have a moving charge, let's just talk positive charge for the moment, moving to the right here, we can define the magnetic field created by this moving charge using what we call the right-hand rule. Right-hand rule. The right-hand rule for a moving charge indicates that if you point your thumb in the direction of the charge's motion, your fingers will now curl in the direction of the magnetic field being created by the moving charge. So if the charge is moving to the right, your fingers curl around this way, so that they're coming up out of the page, down into the page, wrapping around, creating a circle around the motion of charge. So here I'm going to use a couple other symbols. A circle with a dot represents something coming out of the page, meaning my fingers pointing up and out. An X is then going to represent something going into the page, in this case, magnetic field. So we create a magnetic field coming out of the page, then wrapping into the page and around. Okay, so moving charge creates a circular magnetic field around its direction of motion. Creates a circular field around its direction of motion. All right, parts of the right-hand rule again show that your thumb points in the direction of motion of charge. Thumb points in direction of motion, and I should clarify of positive charge. Charge motion. While your fingers wrap in the direction of the created magnetic field. Wrap in the direction of created magnetic field. Illustrating this in another fashion, if I have the current, or if I have charge coming up out of the page, charge coming up out of the page would now be indicated again with my thumb, and fingers wrapping around, creating a circular magnetic field in this direction. Alternatively, a charge going into the page, so this is I here, this is I here, shows that my fingers are going to wrap in the opposite direction, creating a clockwise magnetic field. Yeah, Habiba. So we need to define each of these based on either positive charge or negative charge. And because Ben Franklin already established that we talk about current as the direction of positive charge motion, that convention has just kind of continued, that everything is defined in terms of positive charge motion. So for each of these, they're consistent with talking about the direction of current. But if we talk about the direction of an electron's motion, we simply, like if this were an electron moving, we'd simply talk about it being in the reverse. The magnetic field would be created in the opposite direction. Or you could try to confuse yourself by using your left hand. All right. Demonstrating this real quick. I have a that I'm just going to connect to a couple of wires, run some high current through it, call it good. Whoop, that's a little high. Oh yeah, DC, evidently I exceeded 10 amps and it wasn't happy. All right, so I'm setting this at 4 amps. I've got a wire here. So the red line is connected to the positive. The way we got this set up, the current is flowing in that direction. That means that the magnetic field is going to be created in this direction. So what I'm going to do is I'm going to take a compass and place it on top of the wire And above the wire, the field is directed in that direction based on this right-hand rule. So my red pole, let's see which way. Yep, the red pole of my compass should point that way. Oh, good, I'm not a liar. Sweet. All right, when I move this to the underside of the wire, the magnetic field is now going to be pointing in the opposite direction. So if I turn this, it should just kind of stay with it. Okay? So compass is naturally pointing in that direction. I'm going to now hold this vertically so that my current's going like that. My magnetic field's curling around it. So I should get the compass to point in a circle as I move around the wire. I'm watching the screen to get the frame rate right. Because, I mean, I can see my hands just fine, but I don't know how much it's blurring for you guys. All right. Questions about magnetic field direction created by current? Yeah. Yeah. It's so the magnetic fields cancel. Yep. Because if you've got wire going in one direction, creating magnetic field, if you have current coming in the opposite direction, the two magnetic fields will cancel out. All right. So let's say I want to actually use this magnetic field for something. That means I'd want probably a stronger magnetic field than just a singular wire carrying this. So if I've got a power source, one of the things I can do is simply take that wire and loop it over top of itself, meaning that each one of these loops is going to provide an additional magnetic field as determined by that right-hand rule. So positive end, current's coming that way in the top segment, curling out and around. So I've got out of the page, into the page. Current's then moving over and down, so moving down, into the page on the inside, out of the page on the outside, out of the page. And likewise, as I continue moving around the circle, showing that what I've now created is a magnetic field in which the magnetic field is coming up on the outside and going in on the center. This is what, when we start making coils of wire, in practical use, we call them solenoids. So solenoid is a coil of wire with a magnetic core that can basically be turned on and off to create an electromagnet. A coil of wire with a magnetic core. Cars use them for a variety of different things. Valves in your engines can be used for them. I don't know about the doors well enough to really give you a good answer there. That makes sense. Coil wire of magnetic core with a magnetic core that can be turned on and off. So I've kind of got a top-down view of this. I'm going to rotate my view so that we've got a side view. It's like one of the two things I can actually draw. All right. So what we're looking at here is the same drawing as above. But in this case, I've drawn in a metal core, iron probably, maybe nickel, something like that. But what's important is that typically these are soft magnets, meaning that it's not something that on its own has its own magnetic poles. So like a nail or something that wouldn't normally be magnetic unless you've, or sorry, wouldn't normally be a magnet, but unless you've actually like done something to it. So when the current is off, there's no magnetic properties about this. When the current is turned on, I can then follow the coil and show that on, let's see here, how did I create this? On this side, I'm going to have an M pole, and this I'm going to have an S pole. I could do this by following the coil and determining how each end of the wire is going to wrap, or I could use the right-hand rule for solenoids. Oh, it gets worse. For solenoids. So, the right-hand rule for solenoids is literally the opposite of the right-hand rule for a wire. So, wherein a wire, we showed that our thumb pointed in the direction of current, and our fingers wrapped in the direction of the magnetic field. Now we're going to have our fingers wrap in the direction that current flows around the core. So because this one comes over the top, we're going to follow that over the top. Your thumb will then point in the direction of the end magnetic pole. So fingers wrap in direction of current, and your thumb points in the direction of the end pole. Points towards end pole. Habiba, I saw a hand. No? So my current's wrapping around in this direction. So because this part goes over the top first and current's flowing there, my finger is going to wrap here. My thumb is now pointing towards the end pole of that magnet. Oh, okay. So real thing, for tests and quizzes on magnetism, I almost always find that, first of all, some students don't want to have their hand up moving around because they feel they look like a fool. You only look like a fool if you're trying to do the right-hand rule with your left hand. Second thing, I always find people who are trying to do this with their left hand, I try to catch you during quizzes and tests and say, no, that's your wrong hand. And I totally point it out to everyone that you're using your wrong hand. But on the flip side, then you get your answers right if you're using the correct hand. Okay? So actually use your right hand to actually manipulate your hand in the air to determine what way fields are going. All right, so I'm taking that same pair of wires. I've still got them connected to my power supply, and now I've got a iron core. It's a spike, and a wire wrapped around it, meaning that I've got a solenoid here. Okay, the wire wraps in this direction. So I'm going to attach the positive side here, meaning that my N pole is going to be up here, my S pole is going to be down here. This is a much stronger magnet, yeah. All right, so I'm turning this on, and that's my S pole, so my red side's pointing towards it. This is the N pole, so the white side, whoop, you can't see that. So the white side's pointing towards it. Okay? Because Alan asked if this is a much stronger magnet, we will go ahead and demonstrate that it is a much stronger magnet. Caroline, you were saying, how do I what? My fingers are following the direction the current flows. So because the red line is the positive end, what I'm doing is making sure that my fingers are following that positive end in whichever way it wraps around the coil. You mean like, hold on. How do I know to start from here? Because that's where the red line from the positive end is? Yeah. So I knew I connected the positive end here, so I knew I wanted my fingers to follow that. Oh, yeah, no. All right, so back to Alan's point. Is this a stronger electromagnet? The answer is yes. Okay, if you can see it, sweet. If we want it to be stronger, I just have to turn up the current. Turn up the current. I'm now at 8 amps. The whole thing is vibrating, and it shut off. Yeah, the whole thing was vibrating. Because it's only running at like 20 volt. No, not even 20 volts. I'm running at maybe 10 volts. I have no resistors on here. I just have wire. Say again? It gets warm. All right. Yeah. Aside from just creating an electromagnet, the next piece here that we've got is the electromotive, well, yeah, electromotive force I'll come to. Sorry, it's the force on electrons in motion. Yeah, Alan. So my thumb's pointing in the direction of current. My finger's then going to point in the direction that the end pole would feel a magnetic field. So the magnetic field is a circle that's created. It, saying that it has an N pole or an S pole isn't terribly accurate because it's a circular field. The entire circle is a single direction. I don't want to use the term charge with magnetism because it's wrong. Okay. So it's that it's creating a circular magnetic field around it. That field's always pointing in the direction an N pole would feel a force. So like when I had the wire created, wire creating a magnetic field, the compass just kind of pointed in that direction around it because the negative end was pulled towards basically the reverse direction, and the end pole was pulled towards the end direction. So again, don't think about magnetism as poles or charges. Think about magnetism as a direction. It's like saying if we're driving, you don't talk about driving with the front of your car being a specific object in the back of your. No, I guess you can because you've got a hood and a set of taillights, but you're really talking about being forwards and backwards. We've got to disjoin it from the actual object concept. Which one? What? Because your fingers just reversed direction when you did that. You pointed this way, they went this way. You pointed that way, they went this way. All right. So next is force on a moving charge. Since a moving charge creates a magnetic field, if we have a moving charge in a magnetic field, those two magnetic fields should interact to exert a force on the moving charge. So if we've got a moving charge here, and let's just say it's some positive charge, and I've got a set of magnetic field lines just pointing in this direction, we can determine the direction that this charge will feel force based on yet another right-hand rule. Okay? In this case, we have our magnetic field lines following our fingers. So our fingers are pointing in that direction. Next up, we've got our positive charge moving this way. So my thumb is going to point in that direction. Okay? So I've got my thumb pointing to the right, my fingers pointing towards the bottom of my page. My palm is now pointing in the direction that that charge will feel a force, which is mutually perpendicular to each of those into the page. So in this case, charge feels force into the page. So again, if I've got thumb going that way, fingers going this way, force is that way. In every case, they will create an XYZ axis set. They're all mutually perpendicular, yes. Okay? So motion of charge and force must be perpendicular to, or sorry, motion of charge and the magnetic field must be mutually perpendicular in order to actually even generate a force at all. So magnetic field Yeah, I'm going to do that too. Yeah. Magnetic field and charge motion must be perpendicular for force to be exerted. Okay. So again, that was fingers are magnetic field. I'm just going to write B field for short. For some reason, B is the letter we use to represent magnetic field. No, I have no idea why. Oh, well, there we go. Right? Okay. So your thumb, yes, points in direction of positive charge motion. Yes. And then your palm will face in the direction of the force the charge feels. Palm faces direction of force. Is the electric motor. So an electric motor uses an existing magnetic field and a coil of wire inside that field. Yes, it does. And I'm just going to talk DC motors here. That wire is then through a couple of what we call armatures connected to a voltage source. And for me, the voltage source will be oriented like that. So I've got the positive end on this side, positive, negative end on this side. Current now can flow up, through, around, back down to our voltage source. We can use this third right-hand rule to determine what this coil of wire inside the magnetic field is actually going to do. So as our magnetic field moves up here, thumbs pointing in the direction of current, fingers are pointing in the direction of magnetic field. This segment of wire now feels a force into the page. So into the page, represented by X's. Current, because I drew arrows pointing in the direction the magnetic field is. What do you mean? Because current's flowing out of the positive side. Okay, so I get to this side, current is now flowing down, magnetic field is pointing in that direction, so the force that segment of wire feels is pulled up out of the page. Because these two are in opposition of each other, this coil of wire will now spin like that. It's a motor, yeah. Isn't that what I said like 3 times? All right. Question for you. Direction of force on this segment. Not even negligible. 0. Direction of force on this segment. Why are they 0 in both cases? Right, they're not perpendicular, they're parallel. All right. Let's do that demo real quick.